So I'm going to introduce you our speaker for today. He's Omer. He's manager for our TikTok Global Live Wallet team. And then I'll allow him to walk you through his background as well as give you an introduction to databases today. All right. So welcome, Omer.
Hi guys, hello. Thanks a lot for joining this session. And Carmen, thanks for pointing out the typo in slide 11. I did fix it. I apologize for it. I did the slides a little bit late at night. Okay, so let me start the session. And give me a second. Give me a second. Sorry. Let me share my screen. Okay. All right, I hope you guys can see my screen. Give me a reaction or give me a hand raise or something if you guys can see it. Or let me know in the chat.
Yes, we can see it.
Okay, great. All right. So hi guys. Before this session is going to be about databases, and let me just introduce myself a little bit before I begin. So who am I? I'm Omer. I graduated from NUS in 2014. I'm a computer engineering major there. And actually my background, I actually started career doing iOS engineering. So I was an iOS engineer and I worked in Garena in C for around 4 years. I worked on a couple of apps there. One is called Garena Mobile, one is called C-Talk. So I did iOS engineering for 4 years, went quite deep into iOS actually. And after that, I just kind of decided to venture out a little bit. Also we got a new project, so I got an opportunity to do a lot more things. So that time Garena was starting a live streaming project, something similar to Twitch. So I worked on that. I led that project actually, and when I did that, I wore quite a few hats. I was a backend engineer. I was also SRE. I was a web engineer as well. I also did iOS. So kind of full stack for this project, and I worked on this project for around 4 years. And until we decided to close this project, and then after that, I decided to jump to TikTok. And at TikTok, I'm currently leading the wallet team. And some of you might wonder, what is wallet exactly, and what is this? Why is wallet what you call? Why does TikTok have a wallet, right? Like TikTok being, TikTok being what it is. Like why is there a wallet there? And just to give you some idea what this does is when you're live streaming, right? One of the things you can do is you can send gifts to streamers, send gift to your favorite creators. And this is actually a major revenue source for those creators. And the way, and basically controlling this entire process from users, allowing users to do the top up, so they can top up their account, so they can then send those gifts to creators. And later on, creators can receive those gifts and actually withdraw the money out and actually draw to their bank account or whatever payment method they prefer. All this system is actually handled by what we call the wallet team. So it's quite an important system. It's very important. I mean, it's important for revenue. It's important for revenue, both our revenue and also the creators' revenue. And it's a system where correctness is very, very important and stability is very, very important. And we deal with databases a lot. So you can imagine that. So databases are our bread and butter. And so for our team, like if you do interview for our team, like we do ask a ton of tough database questions in our interviews, because we expect people to be good at databases so that they can because you need to be in order to do well in this team. Like a bad database query or overloading the database unnecessarily can cause a severe incident. So yeah, that's just give you some idea what we do. So for myself personally, I mean, aside from working on tech stuff, I love history. I'm a big fan of history. I actually just came back from Italy from a 2-week trip which is for me was a deep dive into ancient Rome. And I also love anime. I also really enjoy distributed systems in general. So if you're interested in distributed systems, feel free to hit me up. I really enjoy thinking about edge cases that can happen. Okay, so that's a little bit about me. So let's get on with the main content for today. All right, so when we talk about databases, right, let's first think about what is a database, right? If you break a database down into its components, like what is database? And you guys may have dealt with databases before, maybe maybe you've used SQL, MySQL, or SQLite, or MongoDB, or whatever. In general, databases, no matter what kind of database you use, in general, it can be broken down into like the following bits of functionality. So at the top layer, normally, so a database would have some kind of interface or query language, right? So that you can actually use that database. And many databases that use SQL would, for them, this query language would be SQL. And there's in the last 10 years, there was sudden hype about NoSQL, where we had some API-based query languages, which are also present. There's a document layer kind of style of queries, or there might be a graph-like query language, etc. There's many different kinds of query languages, but the key idea is there may be some kind of query language in front. And normally, when you deal with the database, you deal with this thing directly. And what this thing normally talks to is some kind of query processor. So the query processor's job is to convert that query into something a little bit more meaningful, right? And to convert it into some instructions, or convert it into some kind of plan, so that the database can then execute that plan and talk to the other necessary components it needs to. And what are those components? So normally databases would have some kind of metadata store. It would have some store for the actual data that it needs to keep the records that you're actually storing inside. So there'll be some storage engine that keeps track of that. There will also be some indexes, which will help you look up data faster. So these are some common abstract components. And normally when you run a query, you'll go through these steps. So you'll first parse and validate the request. You'll create some execution plan. Ideally, you want to use some indexes here. You would read or update your storage, update your metadata, and then compute and return the results back. Normally, this kind of pattern applies to almost all databases you can think of, right? And generally, like, this is the kind of the lens through which you'll be looking at databases today, all right? And within databases, normally there's two wide categories. So databases are a very rich field with hundreds, thousands of databases actually. But like realistically, there's probably tens of databases you can choose from. There's different databases with different kinds of workloads. It's a very important, so a mark of a good software engineer is to use the right tool for the right job, right? And databases are quite similar. Different databases are optimized for different kinds of things. And one broad category to distinguish the different kinds of databases is by workload and what kind of workload you're doing. And the most general way to do this is basically defining whether your workload is OLTP or OLAP. So what do these two terms mean? OLTP means online transaction processing. All right. So and what that means is transactions, OLTP transactions are transactions that will capture and store and process small amounts of data, but lots of them. So normally you'll be doing processing of individual records. And some use cases of this may be, for example, you're updating someone's balance, for example, or you're requesting someone's item in the feed, someone's feed, for example, right? So these are individual records, maybe an individual user's data, and your processing is a small amount of data, although the term small is a little bit arbitrary. The key idea is that you want some result in real time, and you're and the amount of data you're going through is not that large. That's one category. It's called OLTP, and certain databases are designed for this. We also have another very different kind of workload called OLAP, which usually means you're analyzing and you're aggregating through a huge amount of most likely historical data. And basically over here, the difference is in terms of the large amount of data you're processing, and also the complexity of the query you're executing. So if like if you were to draw a graph, which I probably should have done here, there's two axes. One axis would be the query complexity, another axis would be the data size. And the extreme for this, the top right hand corner of this would be OLAP, and the bottom left corner for this would be OLTP, basically. And then you have different databases that are fall differently in this spectrum, but they're clustered. So for example, MySQL and SQLite, Postgres, these databases are very good at OLTP, for example, MongoDB as well, Cassandra, etc. as well. OLAP databases, some examples top of my head I can think of would be things like ClickHouse. Spark is not exactly a database, you put it on top of Hive and use it for OLAP queries as well. There's many different kinds. Yeah, this just to answer a few of these points. Okay, so that's couple of there's the two broad categories just to share. I do have some quick questions which I'll just quickly answer. So there's a question on, does TikTok use structured or unstructured databases? And to answer this, actually, to be honest, it really depends on the scenario. Most of the time, most commonly, we will use structured databases. And personally, my preference also is structured databases. And the reason for that is normally the use cases where you think you need unstructured databases, they end up being like, you end up having some kind of structure there anyway. And normally you end up wanting to optimize the query performance for those use cases eventually anyway. And if you want to do that, going structured from the get-go is usually much easier rather than adding it later on. There are some edge cases, right? So it depends, but mainly, maybe most of the time, we will tend to use structured databases. And okay, so another question is how to integrate PyCharm executions with a sync data source. So for this question, this depends on how you're using, because PyCharm is an IDE, right? It's not it's not the language, it's not the thing itself that's using database. So normally you would need to write some code to import your database driver, and then you need to set up a database server on your machine, and then talk to the database, configure the database driver in code, and then basically run that. That'll how you talk to the database, right? Okay, hope I've answered that. And OLTP, another question is OLTP is for less intense amounts of data compared to OLAP. That is exactly correct. So OLTP, the amount of data is usually much smaller. And objects, so another question is on object storage. Are they counted as a type of DB? Yes, they are. So MongoDB is an object store, as I mentioned, and this is indeed a kind of database. And there are many others as well. And actually, MySQL and other these SQL databases also support object storage. So they have a JSON data type that you can also use if you want to do both. So this is a common thing, and yeah, it's definitely a database. And there's another question on the large amount of tables that we have and how do we do joins. This is a great question. I'll talk a bit more about this later on, but in general, I'll just answer that the way we do joins is we don't do joins, right? So so generally when we are using when we have OLTP use cases, we'll try to keep our queries very, very simple. And one of the ways you keep it simple is you avoid joins. You can avoid joins by doing, you can avoid joins by basically duplicating the data if you really need to. That's one way to do it. Another way is basically you can have do what's called an application layer join, right? So instead of joining a database, you can join in your API where you finally need to aggregate this data together. So we have several strategies to do this, but generally speaking, on the database layer, we generally tend to avoid SQL joins at the query level, especially for high frequency workloads. Okay, all right. So I've answered a few questions here. I'll proceed. All right. Okay, so talk a bit more about OLTP and OLAP, right? So there's okay, so what's the difference, right, between these two, and why does this make a very big difference in terms of architecture, storage architecture? Actually, the main reason why, and one of the reasons why, is actually the design of the storage system it really depends on, if you really want to design the storage system well, it really depends on the workload. So in OLTP systems, normally what we'll do is we would use what's called a row-oriented storage system. That means when we are storing data, we're storing the rows together. So the rows are located together spatially. So what you get is a sequence of rows, something like this, basically. So you'll have all these rows that are stored together. And what this allows us to do, and the nice thing is that we get very fast reads and we get very fast updates, right? Because for row reads, you have the whole row there. I can read one row very, very fast. I only need to do one fetch. I can read my row very quickly. All the data within one row is together. So if I have a row with several columns inside, all the data is there. I can just access it directly. I can also update it in place. It's very fast, right? So I can actually do this quite well. And this is normally how many databases or many storage systems that are OLTP based are usually designed around row-based storage. However, if you think about OLAP kind of workloads, the more common design is actually to store columns together, right? And what that means is, and just to share, like in this example, sorry, just to share, the D1, P1, S1 are the columns. So I have in this table, I have 3 columns: the date, product, and sale, and I have several records, right? So D1, P1, S1, D2, P2, S2, and so on. These are each rows. So in the row-oriented storage, you can see the D1, P1, S1, all the row 1 data is together, all the row 2 data is together, and so on and so forth, right? Another way to organize this data is to use what's called a column-oriented data store, where I actually store the columns together, right? So I can actually store the dates, what you call so all the dates are stored together, all the products are stored together, all the sales are stored together, etc. And there's several advantages from doing this. One very big advantage is that I can actually get much better compression. So because a lot of data looks similar, the compression, I can apply some fairly sophisticated compression algorithms to get very good compression. For example, if you have time, imagine that all these dates are just 1 second apart, right? All these times are 1 second apart. I only need to store the diff, and the diff is very small. I only need a few bits to store the diff. So I can actually have some very sophisticated strategies here, and the amount of space I would take is quite tiny. And if you think about it, there are some other use cases that benefit from this as well. So if you're, for example, if you're dealing with a time series database, right, where you want to store something by time, normally you don't want to use MySQL for this, because MySQL wouldn't be that good, especially if you want to do some complex queries. So in that case, you would use something like a time series database, and time series databases often would use some kind of column-oriented data store, and they would use this kind of strategy to optimize the space they're using. So Prometheus, for example, uses this strategy. OpenTSDB also uses something like this, and many other TSDBs will use something like this to kind of get a better performance. All right, I hope that makes it a bit clear. I got a few quick questions. I'll answer these quickly as well. So one question I got is, does duplicating data over joining tables create additional storing costs? I mean, of course it does. It's everything's a trade-off, right? So in this particular case, if you like, so between normalization and denormalization, although it really depends on the, like, specific trade-offs really depend on the specific use case, but often more than not, the storage cost is usually something we can bear compared to the compute cost. So normally compute cost is more expensive. And another pretty good question I got is, that doesn't joining an application slow down the app, and read replicas wouldn't work because data is real time and replicating eventually consistent. So it's a pretty good question. And like I said, this really depends on like a specific scenario. So on exactly what you're trying to do. So like, for example, if it's a one-to-one kind of join, it doesn't matter that much, right? But so it really, so in this case, depending on what you're trying to do, what I would do is, in this case, I would design the API in such a way that this is straightforward. I think to have a more detailed example, it would be helpful to have a more detailed example for this, so we can deep dive into this, and maybe we can do that in the Q&A section. But I just want to highlight that this is a pretty good question, and the exact trade-offs really depend on the specific problem. So another quick question is, column-oriented data store require duplication of primary key? No, actually, they do not. Column, so the way they handle they don't store the primary key in a duplicated way, actually. They have this concept of a record ID kind of thing, and they use kind of offsets to measure this. So within each column, they'll know the position of the row, and they'll kind of they'll know that, and then they know how to do the lookup using that. But bear in mind, that's also why columnar stores are not good for updates. They're actually quite slow to update. So there is a trade-off. The read performance is super fast. They can do very complex queries, but the trade-off is their write performance is usually not that good, especially for updates. Usually writes for appends and inserts usually are okay because they're sequential, so it's a little bit different. Yeah. Another very good question is, can I say column databases are part of a time series database? Actually, I would say they are different sets, but there is time. Usually, the time-oriented databases are like a subset. Maybe some exceptions. Maybe some use row, but none that I know of. None of the famous ones that I know of. But they are kind of, they do have a very large overlap. And another quick question I got is, OLTP same as horizontal partitioning? And not at all, actually. These two, horizontal and vertical partitioning, are completely different things. I'll talk about these separately. Or just to give you a brief idea right now, horizontal partition just means that you can add more machines to scale something horizontally. Vertical partitioning means the only way you can scale out, the only way you can improve the performance is you add a better machine, a machine with more cores, right? But that's a completely different thing. And usually OLAP and OLTP are, there are some OLAP DBs that will support either of those, and some OLTP would support either of those. This really depends. All right. And another question I got is, how do you implement OLAP, OLTP, or OLAP? I'll talk more about this in a little bit. So wait a while. All right. Okay. So we talked a little bit about this. Talk briefly about data models, because so different storage systems have different data models. In this talk, I'll focus more on the relational model, which is what we use mostly, and it's kind of, in my opinion, and in the opinion of many other people smarter than me, it's a very strong model. And it usually models many scenarios quite well. There are many other kinds of models as well. There's key value stores, which are very common and very popular and very fast. There's graph models, there's document object models, there's wide column, there's array, matrix, vectors, etc., which has become quite hot recently with a lot of AI products taking shape. But we focus this talk on relational model. And if you guys have any questions or for other models, do feel free to ask me. Okay, give a very brief introduction to relational model. Many of you guys may have studied this in school, and it's not that hard to grok, to be honest. But I think the key idea behind a relational model is that in our database, we will just store these simple data structures. We call them relations, aka tables. The key principle here is that the physical storage, how it's actually stored, is actually left to the DBMS, to the database management system. The DBMS or the DB will actually decide how to store it. The application layer does not control this. Application layer only talks to the DBMS by using some high-level language. In many cases, this is SQL, all right? And normally this relation, aka table, is basically an unordered set that contains the relationship of attributes that represent each entity. So a tuple, which is a row, is basically a set of attribute values. And normally the values will be some kind of scalar values, and normally in most databases will have some kind of null value. All right. So this is the kind of more mathematical theoretical definition. I'll show some examples later on. Got a question on what's the difference between a relational and non-relational model. So the difference between a relational and non-relational model is that the non-relational model doesn't use relations, right? So normally, I'll give you a more concrete example. So a key value store is an example of a non-relational model. In that case, the model of key value store is just keys and values. You're storing a key and a value, and that's it. You don't get anything else. A key is a set of bytes, a value is a set of bytes. That's all. That's the only model you have. So everything you want to model, say you want to model a user, you have to make it fit into key value model. Normally, maybe your key will be user ID, and your value might be a JSON struct representing the user, for example, right? So that's one way to model it. Another kind of model might be a document model. In this case, your model would be a user. In a document model, your model might be a JSON document containing the user attributes in JSON format, for example. So that, and you may have some nested attributes, for example, nest the model as the document, right? In a relational model, this would just be some table called user. We'll have some columns like ID, name, age, blah blah blah. All right. So I hope that kind of gives you some idea. So Kaishwan asked a question on is it accurate to say indexing is done on OLAP rather than OLTP? Is easier done on OLAP rather than OLTP? No, not exactly. That's not true. And normally, actually, OLAP does not require indexes normally, and that's because in OLAP most of the time you're scanning through a very large amount of data, so indexes are not that useful. For OLTP, indexes are very important because you want to do lookups for single rows very fast, right? So that's why indexes are very important. But in OLAP, you're scanning through the whole damn thing. So normally you don't really care about indexes that much. And then you do care about them to some degree, and there'll be some optimizations, but that's not usually a major concern. And there's a pretty good question on unordered set. And does indexes make it ordered? So this depends on the query, right? So if you normally, if you can have an order by clause in your query, and then it'll be ordered, and then you can have an index to order it, that'll speed up the query. But theoretically, some database, the database theoretically is supposed to store it unordered. So what ends up happening, however, in reality, is the performance of this thing depends. So in Postgres, for example, they store it as unordered. In MySQL, they don't. In MySQL, the way storage engine works is it actually uses the primary key as an index, and it'll store everything using the primary key. So so that's why primary key lookups will be quite fast, and it is actually stored in an ordered way. But the key idea here is that what I mean by unordered is at a theoretical level, at a logical level. In a DBMS, you're not supposed to care about the storage, right? Because that's up to the DB. At a theoretical level, it's unordered, and that means that you need to specify an order by clause if you want to get the result in a specific order. That's what it means. You can't rely on the order given to you by the database. All right. I hope that answers your question. All right. Okay. So talk a bit more. So one very important column, and some of you guys already alluded to this, in a database is called a primary key. And a primary key's responsibility is to uniquely identify a single tuple or row. And normally many databases will give you this ability to automatically create an internal primary key. If the table does not define one, this depends on different databases. In MySQL, you can specify a table, a primary key, and specify a type as auto increment column. So it'll use auto increment, it'll auto increment, and then it'll be guaranteed to be unique. And so there then, and yeah, so primary keys are quite simple. Okay, another question I got is, are indexes stored apart from actual records? This is a really good question. I'm going to talk about storage engines later on in a bit more detail, but just to briefly share, it depends on database, but in most databases, yes, they'll be stored separately. And there's a separate data structure to store them. All right. Okay. All right. So going on. So aside from primary key, we also have this thing called foreign keys. So in this simple kind of table schema example, a foreign key basically is some kind of ID that'll refer to another table's primary key, or another column in another table, not necessarily primary key. Right, this is how we build relations between different tables. So in this case, for example, we can see we have artist, we have album, and we have artist album, which gives us the relationship between an artist and an album. In this case, the relationship, so the relationship is like a many to many, like one artist can have many albums. So yeah. So like keep that in mind, right? So this table contains like this relationship between these two. All right. There's a good question on explaining the what I meant by the logical key. What I meant by that is what by logical I mean what you as the application developer need to worry about or need to care about. So when I say logical ordering, what I mean by that is when you type SQL code and you do a select star from artist, and then you get a result, that result will be ordered arbitrarily. And by right, you should assume it's unordered. That's what I mean, because you should not make any assumptions on how it's ordered. Now, internally, if you're using MySQL, maybe it's ordered by primary key, maybe it's not, it depends. And MySQL has the right to change that. So if you do the same query from Postgres, you get a different result. And if you want ordering, you have to specify order by. So if you want to order by, if you want to select star from artist, order by name, then you'll get the result ordered by name. So my key idea when I said logical ordering is if you don't specify order by clause, you cannot make any assumption on how it's ordered. All right. I hope that answers your question. If it doesn't, feel free to type in the chat. All right. Okay. Another question I got, pretty good question again, is it preferred to store nested objects in SQL or the flattened data? I'm not sure what you mean by nested objects in the SQL, although I guess what you mean is serialize the object in some kind of JSON blob or something, I guess. Or do you mean like as a relation? Normally, if you have a nested hierarchy, usually what we end up doing is either you'll store it as a blob, or actually what happens is many storage systems like MySQL actually support JSON, and they actually support querying JSON as well. So you can actually store nested stuff in JSON as well. And that's what I recommend, especially if you're using a later version of MySQL. Another question on primary keys versus indexes. This is a good question. There is a difference. So difference is primary key is usually always index, but indexes are not only primary keys. So you can have indexes on other columns. So for example, in this case, I want to have an index on the name because I want to speed up queries on the name. I can add index on the name, and then my queries for the name will be much faster. All right. I'll talk a bit more about indexes later on, so that this part should be clearer. And I got a question on graph databases. Do we use them? Yes, we do. We do use them for many different kinds of use cases. Recommendation is one of them. but I don't have that much detail. I don't have that much to share on graph databases right now. All I can share about is, yeah, we do use them a lot for many different kinds of scenarios. Yeah, and I got a question on what is flattened data. I actually don't know, because this refers to the question. I'm not 100% sure what they meant, but I gave two possibilities on what they could mean, and let me know if they weren't clear. Yeah. All right. Okay, moving forward. So here's an example database I created. So let's say we have this is a course, and many of you guys are students. You know, we have let's say we have a database with students, a table called students, which has student ID, name, login, GPA. We have a course, right? These students can enroll in a course. Here we have a course ID, we have a course name in this table, and we have a table that stores the relationship between these two things. So we have an enrollment table, stores the student ID, course ID, and it stores the grade that they got for that course. All right, very important, right? Okay, so let's say I model my database this way. Imagine this, and we'll use this database for some fun stuff. All right. Okay, so first thing that comes up is, okay, so how do you create a table, right? So anyone want to type in the chat? Like, anyone know SQL? Like, anyone? I'll give anyone a try, right? So do you guys know how to create a table? How do I create a table? Let's say I want to create my student table. How do I do this? Anyone want to try it out? You can type in the chat. Yeah. Feel free to try it out. I'll give you guys a few seconds. All right, people are shy. Yeah, create table. That's correct. Create table. Absolutely right. That's absolutely correct. So create table. Absolutely correct. It's very simple, right? So create table. So I create table student, right? And then I just specify specifics for the column, right? It's very simple. So very good. And normally in this case, I would specify that I can specify the nullability characteristics. I can also specify how much space I want these fields to take, right? So for varchar, I wanted to take 255 characters, for example, and I can specify whether I want them to be null or not, and I can specify some default values, and I can specify the primary key. All right, so it's quite simple, very simple. All right, so fun stuff. Let's do some like simple quizzes, right? So let's say I give you guys a question, right? So I want you guys to share with me how do I get all the student names and ages where GPA is greater than 3, right? So how would I do this query? Anyone want to give it a try? Select star. Yeah, select star, but you also need, yeah, that's correct. Select name. Yep, that's correct. That's absolutely correct. So this was easy, right? So, hey, shit, I realized I realized I made a bit of a mistake in my slide again. Okay, never mind. All right, but yeah, that's correct. So we need to do a select name age versus GPA is greater than 3. All right, that's absolutely correct. Cool. All right. And I got a question as well on why do some textbooks put constraints to prefix primary key in SQL. Sorry, I don't understand what you mean by that. Maybe you give an example in the chat and I'll be able to answer. All right, and given the option of SQL and ORM, which is better in your opinion? This is one of those questions which is quite opinionated. And there's different opinions. In our company, we tend to use ORM, though we've customized it a fair bit. I have some mixed opinions on this, and my opinion on this is that it's it really ORMs make it a good ORM is fine, but sometimes ORM make it too easy for you to ignore the query specifically and write bad SQL. So it's important for you to understand what is the SQL they are generating. So I think ORM, while they're convenient, so you do need to use them cautiously, and you must be aware of the kind of SQL they're executing, especially in a production scenario. Yeah. So the performance, ORM performance is usually not an issue. are normally not a bottleneck. So, and might even be sometimes better, depending, because normally you do some kind of string insertion or string creation. Normally, it's not normally that good. With ORM, you can actually do a lot of funky optimizations as well, because you're generating the SQL. You can actually pre-compile it, etc. There's a bunch of optimizations you can do. So performance is usually not the issue with ORM. Yeah. All right, and I got some more detail on the constraint on the question. Yeah, where you add a constraint using on the key. Let me double check this and get back to you. Yeah, let me get back to you on this. I forgot about this, so let me get back to you later on. All right. Okay. All right. So here's another quick one. So another kind of quiz kind of question. This one is a little bit more tricky, because remember we have two tables. One is a student table. One is a course table. So if I wanna get all the student name, GPA, and grade taking this course called database systems, how do I do this query? Anyone want to give an answer? And just to share the schema again, here's the schema, right? So the question is, I want to find all the students' name and grade that are taking this course called database systems. So how would I do this? Anyone want to give it a shot? Yeah, this one might take a bit more time to type. It's slightly long. Yeah, I mean, so yeah, that's correct. You need to do basically you need to do an inner join. So that's absolutely right. You basically need to do a join. That's the key point here. All right. So yeah, you basically need to do a couple of joins. You need to do inner join on then using the enroll table, and you need to then you can do a select where query. So yeah, Aaron is absolutely right. That's the exact query. That's absolutely correct. All right, cool. So basically, yeah, there's different kinds of joins. So if you guys Google for join types, you'll see this image, and this image is usually quite helpful. I sometimes forget which one's which. But I think the key idea is, so inner join basically is a set intersection. And normally if you have two tables, you do an inner join, only the records that match the what you call the join condition. So just to share, there's a couple of things you guys forgot from this. You also need to specify join on what, right? Because so in this case, you need to specify the foreign keys. So in this case, in this query, I specified the student ID. So for a student and enroll table, you need to join on the SID, and for the course table, you need to join on the CID, right? So that's how you specify how to do the join, right? And the reason it's inner join, and why inner join, what's the difference between inner join and other kinds of joins, right? Is different kind. The meaning is different, and this makes a difference depending on your use case, right? So for example, if you have a scenario where you want to get where if let's say you have students who are not taking any course, but you want them inside your data, then you cannot use inner join, because inner join would basically not give you the results, because inner join will only give you results where both of the tables have that value. But if you want to do what I suggest, what I want, which is basically you want to get all the students, and maybe some don't have a grade or some don't have a course enrolled, then you should do what's called a left join, where the left table might be the student table, for example. In that case, you will get everything from the left table as well as the stuff that's in the match records, right? So it's basically when you think of joins, you need to think about sets, because once again, everything is a set. So inner join is set intersection. Left join basically means it's basically the left set, basically, right? Everything in the left set. And then right join is basically the same as left join, but it's everything in the right set. And full join, normally I don't see people use this much, but basically it's like it's basically a set union, right? So it's either this union of these two sets. All right. So that's usually how I think about it, and that's usually a good way to think about which one you need. Most commonly, you probably use inner join or left join or right join, depending on your query. Normally, I've seen inner join or left join are the more common ones, right? Okay. So I hope I've answered this question on left join and right join. Do you prefer to use join or a comma to join tables? Generally, it's better to use join, so you're kind of specific on what you're joining on. That's very important. It affects your query. And do you prefer to use inner join, or you mean inner join on a? What do you mean by inner join or a.id? It could be a.id. So that's usually when you do a join, you have to specify or it's much recommended to specify the join condition, right? What are you joining on? You have to specify that, or it's better to specify that at least. So my recommendation is you do that, please, right? And the question is, should I use join instead of inner join? So that's a good question. So it's kind of the other question as well, like what's the default? Default is inner join. So you can use inner join, or you can just use join, it's fine. Join will default to inner join because it's usually what people want to do. But my recommendation is being explicit, right? So I prefer better to be explicit rather than implicit. So if I were you, I'd just use inner join. Do we use nested selects? So I mean, yes, you can and you should if you acquire use case demands for it. Normally, would I use it in a OLTP use case? Normally, no. Although I would avoid it, especially if it's production kind of use case. But I would use it a lot in an OLAP use case, a lot. So it really depends on use case. It's and kind of what kind of setting we're doing this in. For if it's a low QPS kind of thing where I don't need to worry too much about system performance, then it's okay. I may do a nested select or nest up query or something like that. That's totally fine. It's totally okay to do it. It's just that you need to be mindful of the performance of the query, right? So sometimes you have no choice. You have to do it. Normally, we do it more often in OLAP kind of use cases. All right. What's the default join? I already answered that. It's inner join. I also answered the subqueries, so I'll mark this done. How often is joins used in TikTok? Like I said, it depends. So OLAP kind of queries a lot, all the time. As usually all OLAP queries use joins all the bloody time. It's very, very common. OLTP normally is more rare, and normally we'll avoid it. All right. Why OLTP use most nested? No, OLAP use most nested select. So OLTP does not. The reason is for OLTP, the queries are small, and we try to keep them more simple, not so complex. That's why we prefer not to. For OLAP, where the data size is large and the queries are usually more complex, we tend to use a lot more nested selections, right? I've got a question on stored procedures. Stored procedures are basically when you can configure functions inside the database. It's not in TikTok, it's not that common. However, and normally this is more so because the DB support usually is not that good for this. And but it depends on the database. For MySQL, we tend not to in general, but it depends. There may be some use cases that do. Okay, all right. Okay, so I'll share some. Maybe I'll skip through some of the. Let me share some interesting one, because I think some of these they have some more examples of this. I'll share a quick example of a group by, because we can do group bys. So we can actually group data by some column, and here's an example of that. So basically we can do, for example, if you want to get the average GPA of students by course, we can select the course ID and average GPA, and then we can do a join on all the tables that we have, and then we can group by the course ID, for example, over here, right? So, okay, here's the interesting one, which I think is a bit more, there's several ways to do this one. When I've been thinking about this, I found this a bit challenging myself. So I thought this was an interesting one. So how would you find all courses that do not have any enrollments? right? So I want you to find all the courses that do not have anyone inside. So here you can even answer, and yeah, okay, it does not exist. Yeah, actually that's correct. So not exists, not exactly not exist. Not exist is designed for this. Very good. So I have not used not exist for a long time, so I forgot about it when thinking about this. So I thought of another solution, but not exist is correct. So not exist is the right way to do this. Absolutely right. Okay, cool, great. Um, got a question on does TikTok use in-house DB or data warehouse? Are they available for everyone to use? We use, it's okay. We have a lot of abstractions when it comes to our own infrastructure. For MySQL, for example, we do use MySQL, but we actually have a fork of it. And we have a platform on top of MySQL that supports horizontal partitioning and automatic sharding and high availability, because MySQL doesn't have a lot of those things built in, but we build a system around it. So that's what we use. And for that system itself is not available for public, but we have an open, we have another version of it that we sell to people if you're interested. It's called Volcano Engine. You can check it out. So Volcano Engine is our kind of, it's like, you know how Google had Google Cloud, and then Google Cloud, they sell it to other companies. So we have the Volcano Engine is that thing for ByteDance. So you guys can check that out if you're interested. Internally, we have an internal system, which is a little bit, which is quite different. It's kind of more optimized for our use in-house. That's usually the case for most big companies. Okay. All right. So another question is it preferred from logic on the data and backend code? Absolutely. Normally, most of the time, and this is generally strongly preferred, we put the backend, we put most of the logic inside. The logic of, especially doing RPC calls, most of the application logic would be on the backend code. However, the query part or dealing with the database engine will be still in SQL queries. And these queries normally will be relatively small and not doing too much work. All right. Okay. All right, so I got another good question on is it true that OLTP databases do not adhere to Moist code normal form for both performance, while OLAP databases adhere to it to minimize data size? I'll be honest, I don't know what the Moist code normal form is right now. If you can share a bit more about it, I'm happy to have a discussion about it. I can do a quick Google. Well, I'll Google it in a little while as well. But I'm not sure what this is, to be honest. But you can, if you want to share more information, do share. I'm very happy to find out more, and I'll look it up. I'll look it up later on as well. Thanks. All right, got another question. This was a repeat question. What type of SQL do we use? I answered it depends. Most or many use cases we use MySQL. It's the most common one, but we do use other ones as well. Okay, all right. All right. Okay. Boy's code normal form is about splitting one big table into multiple subtables to minimize data being repeated. Okay, I see what you mean. Right. Okay, I see what you mean. Okay, right. So when it comes to normalization, to be honest, we tend not to be very anal about it. Let's just say that in a production setting, we care more about the query performance rather than the normalization and optimizing the data size. Normally we care more. So normally what we might do instead is we may keep, it depends, but if it makes queries faster, maybe we'll prefer to keep it in one table, right? Especially if it's all being accessed there and we can avoid those unnecessary joins. So we prefer to put in one table. It depends though. So for example, if you have something like some kind of nested field or something like that might be updated separately, in that case you can't avoid it, right? So in that case, we would definitely still use a relation. We'll still use a DB. However, we would we may design our API in such a way to kind of delay that join or not have to do that join at the DB layer normally. So one way to do that is to kind of maybe you want to design your API in a kind of RESTful way, right? That's one way to do it. Another way to do it is normally we'll have a bunch of microservices normally, right? And normally, let's say you have a bunch of stuff you want to query, and what you actually need is only a small subset, right, of the data. So what you do is maybe one service will query data for one thing, another service will query data for another thing, and then in the API layer, normally you'll aggregate this data together in application layer and give it back to the user. So that's kind of an application layer join in a way. It's just that we just give the exact amount of data just needed, which is probably quite small for the client. You don't need to join like 1,000 things. You probably only need to join 10, right? And maybe it's more efficient to do this in the application layer. So like it depends on the overall system design, but the key idea that I want to share is that normalization, being strict about normalization is usually not something we care about that much. We care more about the performance of the DB, right? Nice. Another question is, are there automated tools or good practices to evaluate database and schema designs? I don't know of any very good ones. I think there may be some good lint tools, maybe. To be honest, I think it's based more on judgment. There may, although I might be wrong. I mean, maybe ChatGPT is good. I don't know. I haven't tried it for this use case. But I would trust. I would still rely on judgment. Especially for someone who's good at databases. There may be some good online tools, maybe. To be honest, it depends a lot on your use case, man. So on the query pattern specifically. So yeah. Got another question, ORM, and as I mentioned earlier, yes, we do. We use ORMs. Yeah. All right. Okay. All right. Another very fun one. This is gonna be tough. I don't think many of you guys may know this. I'll be surprised. I'll be impressed if someone gives me an answer for this, right? Which is okay. So I want to find the student who got the second highest grade in each course, right? Second highest, not the highest. So how can I do this? Anyone has any idea? This one is a bit more tricky, or I always have to Google this one. Yeah, partition by. That's correct. That's correct. Absolutely right. So yeah. So you can use a rank and partition by. So these are some special functions. They allow you to do aggregations, but over a window of data. So this is quite helpful. And in this case, for example, I can in this case, what I'm doing is I can do a subquery to get the ranking, and then I can just select from that query to get my rank, where rank is 2. So yeah, this is quite helpful. I won't go into too much depth, so if you don't understand it, don't worry. Normally this is quite rare, but this is and normally you don't need to do this, but like I said, we do this more. It's more common in OLAP queries, this kind of fancy SQL. All right. I've got another question on do you usually create schema design from scratch? And yes, we normally create from scratch. Normally, even though we use ORMs, we don't use ORM for the schema actually. We manage the schema separately, and we'll use we have a separate system for that. Like I mentioned, we have a platform, right, for managing DB. The schema usually is in that platform. So this is because schema changes are very, very, we have to be very, very careful with them, because they can have very big impact. All right. Got a question on ERD. Sorry, remind me, what is ERD? Is it entity something? I forget. Please remind me what it is. All right. Entity relationship diagram. Not really, no. I mean, I just look at the code, man. Yeah. Yeah. Okay, so I got a question on partition again. This is just to share partition again. What is partition for, and why use it? Okay, so this is the kind of more advanced. So the reason for using this is if you want to do some, if you want to do some, for example, ranking of results, right? I want to order the results by something, and then I want to rank them. So if I want to order them, and I want to know what is the ranking, right? So then I would use rank, and I can use rank by rank and partition by. to basically get a list of stuff ordered by that thing. So my recommendation is you need to try it out to get a feel for it, right? So don't you try it out, and then you'll understand what this does. It's quite hard to understand otherwise. All right. Okay. All right. So I'll talk a bit more about the fun stuff. All right. Okay. Well, let's answer a few questions first before I go there. So DB guys at TikTok also code with Golang or just SQL? I mean, so the DB guys are the server team, are basically, so normally backend developers, right? They will interact with the DB. Normally most of our code in the backend usually will be Golang code. And so normally we will write SQL queries, but we will write them in Golang by using the MySQL library or use the ORM. So normally in any programming language, you'll have some library that talks to the database, and you'll use that library to write your queries. Okay. And I got a question on Windows OS. May I know the account that is higher admin privilege than the admin account? I'm not very good on Windows, but this thing doesn't depend on Windows, man. This is it depends on your DB. Are you using MySQL? MySQL should be admin. I don't think there's something higher than admin. Yeah. What ORM we use? We use GORM. So the GORM is GoRM. Actually, the GORM maintainer works in ByteDance, which helps. so we have our own version of it, but the fact that the maintainer works in ByteDance is a good, strong reason to use GORM. Yeah. How to detect malware elements, protect localized data on Android phones? That's not a relevant question, so I'm going to ignore that. All right. Why is there inconsistency using SQL and ORM for database access in ByteDance? Sorry, I don't understand what that means. Because ORMs normally will compile to SQL. So the only advantage, ORM is like a higher level API for databases, and they just make some things convenient for you. So the pro is that you have to write less code, or you have to write less code interpolation, or less ugly code. The bad thing about ORM is that sometimes it can be too high level, and the DB queries it sometimes produces may not be what you wanted. So you have to be quite mindful of what is the query you are executing. Okay. All right. So we're going to talk about fun stuff. So this is the second part of this session. One more question on partition applicable for other kinds of SQLite also. Yes, I believe this works in SQLite as well. All right. Okay, so I'm going to talk about storage engines. This part is more fun because I'm a big fan of this. And this kind of talks more about the innards of databases, like how do databases actually work and what's going on under the hood, right? So I feel that's more it's more interesting. It gives you better understanding, and you can actually compare different kinds of databases together, right? So I think that's better. Okay, so in MySQL, we have one major storage engine. It's called InnoDB. InnoDB is not the only storage engine. There's other storage engines as well, like the MyISM. But InnoDB is the default one, and it's pretty good. In 2010, it replaced the default storage engine. All right, and okay. So what is the storage engine, right? What the hell is this thing called storage engine? So storage engines are very interesting. They are basically a storage engine is a framework or a library that actually maintains how the data is actually stored in memory or on disk inside the database, and it also manages how those queries will work, right? And the storage engine normally will have two kinds of data structures to manage this part. The one kind of structure it would have is an in-memory structure, and another kind of structure would be some kind of on-disk structure. And it's important to appreciate the difference between these two things, because in a database, remember, there's some when you're running a database, the amount of memory you're running on is limited, right? Because normally when you run on a machine, on a virtual machine, for example, you'll have, say, 10 GB of memory or maybe 20 GB of memory, for example, but maybe your data size is much, much larger, right? Maybe you'll have a lot more disk. Maybe you'll have 1 TB of disk or 10 TB of disk, etc. And maybe your data set is much larger than your memory, right? So one of the big problems that databases try to solve for you is how do you query things that are on disk efficiently, right? As efficiently as possible, because disk access is kind of slow. And this is going to be a recurring theme in this part of the talk, right? And normally the way this stuff is managed is there's this thing called a buffer pool. So database systems would have this thing called a buffer pool. The buffer pool is this in-memory data structure that is used to store a lot of information, keep a lot of information related to records in memory. We'll talk a bit more about what this information is, but just to share in one word, it's basically a page. It's storing pages in memory. And when you're running queries, normally the relevant pages will be loaded into the buffer pool. So someone asked, is it like a cache? And exactly, that is absolutely right. It is exactly like a cache. It's not exactly a cache because actually it's mutating the stuff and it's updating the stuff. But I mean, the effect, in effect, it is essentially, yeah, it is used in a very similar way to a cache, because what you want to do is you want to optimize the operation on the database, the data as much as possible, right? So you want to make sure that those operations are fast. So you load the stuff you need in memory so that you can say fetch it or update it or modify it as fast as possible. So that's what the buffer pool is basically doing for you. And normally that's one part of it. Another part of it will be the on-disk structures. The on-disk structures have a very different design, because on disk, basically, you cannot store pointers. You cannot have memory addresses, right? Because memory addresses only exist in virtual memory. They don't exist on disk, right? So when you design something to be stored on disk, the design will be quite different. And when you need to think about the file format and how you're going to load it. And when you're talking about loading things from disk, you're kind of limited in what you can do. So that's why there's different kinds of file-based on disk structures. I won't go to too much detail over here, but just to give you guys an idea. All right. Okay. All right. I got a few questions. Let me just answer them first before I go on. So ORM being used similar to Hibernate framework. Sorry, I'm not familiar with the Hibernate framework. Can you remind me on what Hibernate framework is? If it's it looks like an ORM as well, from what I see from a quick Google. So I believe so, but I have not used it, to be honest. So I can't say for sure. I believe there's a question on prefetching. So prefetching is indeed an optimization that buffer pools do to prefetch stuff. This is indeed a very good optimization that will be done. I got a good question on why is it better to implement logic in backend code rather than SQL query. Okay, let me qualify that statement, because let me explain what I mean by that. But within the context of a single query, definitely better to do it within SQL, definitely. But however, within the context of doing multiple, let's say, RPC calls or complex logic, like if do this query, if this query response is this, then do this other query, right? This kind of logic, especially if that logic involves you talking to another service and doing an RPC call to another service, this kind of logic might be quite hard to do in SQL. You could be done. You can be crazy. You can use stored procedures or even fire RPC calls or network calls from SQL if you want to. But in general, SQL is not that powerful. Like, it's not meant to be used that way. So especially not in MySQL. So that's why if it's one query, yes, definitely you should represent your logic and the query engine will optimize it really well for you. But however, if it's like multiple queries and you have a lot of complex logic in between, complex business logic in between particularly, then I think usually it's quite hard to represent it efficiently in SQL. All right. Okay. All right, so coming back to this. All right, so I'll talk a little bit about storage hierarchy. I kind of briefly mentioned this, right? Like, so there's different kinds of storages on your machines. So, the fastest thing on your machine are CPU registers. They are damn fast, followed by CPU caches, followed by DRAM, actually followed by SRAM, the DRAM. CPU cache usually use SRAM. There's DRAM, then there's SSD, HDD, and then network storage, right? And we also have, so normally the first three categories here are what we call volatile storage. So meaning if your device power is off, you will lose the data, right? And normally this stuff is byte addressable. What that means is that if you have the address of 1 byte, you can access it directly. This is because of the nature of virtual memory. That's how virtual memory works. And it's random access as well. So accessing any byte randomly is usually quite fast. However, for non-volatile storage, which are usually a bit slower, and they're also cheaper and they're also larger, normally the way the access works, and this is the way the hardware actually works, is normally you will access things sequentially. Random access normally will be very slow, and that's usually just not in line with how the hardware works. Another very key point that people might often miss is that the non-volatile storages like HDD, SSD, etc., they are normally block addressable. They are not byte addressable. And then what that means is normally when you fetch things, you'll fetch it in blocks of maybe 4 kilobytes, 16 kilobytes, etc. This is the nature of how this stuff is implemented. So in SSD, for example, I forgot the block size, but there's a certain block you address. You don't actually, so whenever you fetch something or read something from SSD, you don't actually read one item. Even if you're fetching 1 byte, you won't actually read just 1 byte. You will read a full block. And for a good storage system, you need to be aware of this. You need to make use of this to make a highly efficient use of the underlying hardware. Okay. So let me let me talk a bit more. Let me go a bit more. Before I go on, I got another good question as well. How do we implement logic containing both backend code and SQL query atomically? This is a very good question, and this is hard to do. Generally, if you would want a database transaction, right? So especially if you wanted to have some kind of logic that traverses multiple tables, then must be atomic. So if you're doing some update that must be atomic, then definitely you must use a database transaction. You have no choice. What to do if you have database transactions that are over different, say, shards or different partitions or over different database systems, right? Maybe it's not the same database system, it's MySQL and Redis. You want to have some transaction between these two and you want this to be atomic. Or maybe it's some backend code that you want it to be atomic. This is a very good question. And in this case, you probably want to use some kind of distributed transaction framework. So there are different kinds of distributed transaction frameworks out there. Some XA is an old one. There's TCC is one. There's sagas, etc. There's many. The trade-offs that you need to think about are some will only give you eventual consistency. Some will give you some will give you proper full consistency. You will need some kind of two-phase commit protocol between these different actors to guarantee that it's atomic. And there's always a trade-off between this and availability, because normally if you have some kind of distributed transaction, you need to make sure all the participants will do it correctly. And if any one participant dies or does something wrong, the transaction will be blocked and stuck. So you'll be in this weird stuck state, and you normally the system will be a bit fragile. So there's usually a bit of a trade-off. But I just want to mention that yes, it can be done, especially even if it's heterogeneous systems, it can be done. But we tend to avoid it. We prefer to avoid it if we can. Normally, if I have such a scenario, I would model it as a database transaction and then try to keep it within 1 DB, preferably even within 1 shard. Okay. All right. Okay. So I talked a little bit about the storage hierarchy. Let's talk a little bit about. So these are some numbers that I hope everyone here should know. This is how big the difference is. Just want to highlight that the differences are huge, right? In these access latencies. So the L1 cache is 1 nanosecond. And if let's say we model 1 nanosecond as 1 second, so that, we model it in human time, so we get a better feeling for how long this is. So let's say 1 nanosecond is 1 second, right? So L2 cache is 4 nanoseconds, which is like 4 seconds. A DRAM dereference is around 100 nanoseconds. So you can see it's around 100 times slower than a L1 cache lookup. That's quite slow actually, right? So that's like 100 seconds, right? That's like almost a minute and a half, right? That's how long it takes for you to do read main memory. So DRAM is quite slow compared to main memory, compared to your cache. And normally, if you're working like low latency systems, the key optimization you're trying to do there is to move stuff to L1, L2 cache as much as possible. And then there's SSD. SSD, which supposedly is quite fast, is like 16,000 nanoseconds, 4.4 hours, right, compared to 1 second. So once again, like this is super slow compared to L1 cache reference. So you can see this things get slower and slower. And HDD is 2 million nanoseconds, which is like 3 weeks. So you access something from cache at like 1 second, access it from HDD is 3 weeks, right? So that's a pretty long time. Network storage is 50 million nanoseconds, 1.5 years. You'll be staying there for a long time. And tape archives, I won't talk about it, it's too long. Right. So my main point here to show you these numbers is the orders of magnitude difference between the access latencies. So if you can move your workload to a faster storage medium, you get a lot of performance boost. So that's something that a lot of these data storage systems will try to do. All right. Another thing I want to highlight is the difference between sequential and random access. So random access, especially a non-volatile store, is always going to be much slower than sequential access. So one very important point for databases is they want to maximize your sequential access. So the bottleneck, remember, because of this, the bottleneck in databases systems is the hard drive or the SSD. It's not, the bottleneck will not be your CPU. The bottleneck, so when you think about like ON or algorithmic complexity, it's no longer about the number of operations, the number of steps you need to do. It's more about how reducing the random accesses, and you want to maximize the sequential accesses as much as possible, because sequential accesses are orders of magnitude faster than random accesses. So in databases, they will try to reduce the number of writes to random pages, so the data will be stored in, so they try to make sure data is stored contiguously, right? So that's also why inserts, okay, so that's also why like some databases that use, for example, okay, this might be going off a bit, but there are some databases that are really good at inserts, and the reason they'll be good at inserts is because they would try to make sure they would basically try to only write write contiguously, or basically only do append only writes when they're writing, and these usually are quite fast. One examples of this would be databases that use LSM trees under the hood. LSM trees are kind of a data structure that some data storage systems use. So example would be Cassandra, for example, or ScyllaDB if you used it. I've used it a fair bit. These databases are very good for writes. Their writes are damn fast that's because when they write, they are basically just appending. So the writes are very, very sequential, and then therefore they are very fast. MySQL and many other Postgres and many other systems, InnoDB particularly, not MySQL, InnoDB in particular. So InnoDB does not use LSM trees, and InnoDB uses B+ trees. I'll talk about those in a little while. They're a bit different. They're not as good for writes, but they're better for reads, and we'll talk about this later on. So why that they do this trade-off is quite interesting, but it tends to be the case that reads are usually more common than writes. But if you have a write-heavy workload, it's something that you need to keep in mind. Yeah. The other thing also is you want to allocate multiple pages at the same time, and so that you can block these things, batch these things together. And the more batching you have, the better throughput you would get, also because of these effects, right? So I'll answer a few questions first. So we've got a question on why would data be written in the random pages in the first place? So I'll give you an example. This is not that hard to imagine, especially, for example, if your data is ordered by primary key, and let's say your primary key is not auto increment, right? Let's say your primary key is some name, something like a name or something, right? And let's say you insert two users, one user starts with A and one user starts with Z, right? So now you're inserting in two very different locations because your data is ordered by the name, right? So if you use auto increment, it's a little bit different. Auto increment inserts will tend to be sequential because they'll tend to be on the same pages. So they may tend to be sequential, not exactly sequential, but kind of at least close. And it's in a page, maybe the same page, which is going to be faster, definitely. So I hope that answers your question. What is the drawback of using sequential write databases? Okay, so by sequential write databases, actually, I'm referring specifically to LSM trees, which are log structured merge trees. This is a specific type of storage engine that are built on top of this. One very common one is called RocksDB, for example, and there's a MySQL has this thing called MyRocks, which is using MySQL using RocksDB, which we actually do use for some use cases. So this thing, there are pros and cons. Like I mentioned, the pro is writes are faster. Another pro is that actually you can optimize the storage space. The con is the reads are slower. And certain types of queries are slower. So you need to be you need to do these trade-offs between reads and writes. All right. Another question is, does TikTok use message queues like Kafka before writing to DB? Yes, we do a lot. We use a lot of message queues. We use many different kinds of message queues. We have at least 4 or 5 different kinds of message queues for different kinds of use cases. Message queues are another very complex systems. They are also storage systems. They also have very similar problems. But one of the things in message queues is that message queues will optimize for sequential writes. So Kafka, for example, the reason why Kafka is fast is because it always writes sequentially. So that's why it can be quite fast. So normally this is not normally an issue, right? All right. Got a question on what is reading, what is writing. So writing means insert queries or update queries or delete queries, and reading means select queries. All right. B+ trees and LSM meant for indexing or database engine implementation. Can we choose which column and table to use one of the above? So this is a good question. And this is actually more about database engine implementation / choice of database engine. Normally, when you create a table, you can specify the database engine you want to use. My recommendation is don't mix. Choose one for your database. You can vary it by table, but you should avoid having joins or operations between different tables, because then it'll be a little bit screwed up. However, it's good to specify, or good to have the right engine for the right kind of use case, right? So I think this is quite important. And generally speaking, InnoDB is good. It's like a jack of all trades. Normally, it's quite good for most things. Especially, it's very good for reads. So normally, most of the time, this won't be your bottleneck. Your bottleneck, if you're facing a bottleneck with InnoDB, most likely your query is not very good. So then you can optimize your query. InnoDB itself normally is quite good. It's kind of hard to fault it that much. But it depends. It depends. Like so yeah. And got a question on one engine for one database or one engine for one schema. Right. Okay. So let me explain. So when you're specifying a schema, you can specify a table schema, right? You specify a schema for a table. You can do a create table and specify the schema. So when you create a table, actually, you can specify the engine there. So you can specify. No, so normally MySQL, for example, will default to InnoDB, but you can specify a different engine there. All right. Okay, how does TikTok handle concurrency in updating data? If you mean within one database, I'm going to talk more about this later on. If you mean across different systems and across different databases, you need to use things like distributed locks. I won't talk too much about that right now, but that's another thing you can do. You can implement a distributed lock, and then you create a lock, get a lock over the data, and then you can update it in different systems. All right. Okay. All right. So I hope so far so good. all right, let's talk about pages, right? So in databases, we have different notions of pages. And so one notion of a page is called a hardware page. So hardware page is what the hardware will actually update or read or write atomically, right? So whenever you're dealing with SSD or HDD, when they normally won't, like I mentioned earlier, they normally don't deal with single bytes. They deal with pages. And normally these pages will be 4 kilobytes. Some you can configure them to be 16 kilobytes as well. Depends on your OS settings and your driver support. There's also a concept of OS pages, because the OSs also have this concept of virtual memory, and virtual memory is also usually in pages. And this is also usually 4 kilobytes. Also can vary depending on your OS. And finally, we have a concept of a database page, which can also vary between 512 bytes and 16 kilobytes. Database page is basically the atomic unit that the database uses to manage its pages. And normally, the hardware page is the largest block of data that the storage device can guarantee fail-safe writes. What that means is, if you write 4 kilobytes, it's kind of atomic. It's it either went through or didn't. If you write let's say 5 pages, you can't guarantee all 5 succeeded or all 5 failed, right? Like if I write like 20 kilobytes, I can't guarantee that either all succeeded or all failed. Some of those may have succeeded, some of those may have failed, based on those 4 kilobyte boundaries. All right, that's just the nature of how the hardware works. Okay. So like I mentioned, there's different concept of pages. At the lowest level, the hardware has a concept of pages, right? So the hardware itself, this disk hardware, has a concept of pages. And that's an abstraction the disk hardware would use when talking to the disk driver, when talking to the hardware unit. They will deal with pages normally. And to model this thing well, the database also will have an abstraction called database pages. So the thing that we're talking about more, that I'm going to be focusing more on, is database pages. But I want to also highlight that the reason why databases do this is because under the hood, there's this thing called a hardware page. And the database page wants to make optimal use of the hardware page. That's why they model this thing explicitly. All right. The reason why they have to do it this way is because they can't actually get the hardware page directly, because they're not actually implementing the disk driver. So normally when they talk to these OS APIs, the OS APIs that deal with block storage systems are quite basic. They can only like to read and write bytes to a particular offset. So it's not a very strong API. So that's why the databases normally will explicitly manage these pages. I won't talk too much about that. It's too deep of a rabbit hole. Okay, all right. Then inside the database, right, normally there'll be this thing called a page directory. So these are some special pages that keep track of the location of all other pages. Now, where is this page that has this data, right? So it also keeps track of the metadata, like what are some of the free slots on the page, and where are the free and empty pages. And the database will make sure that page directory is in sync with the actual data on the pages. All right. Okay. Let's talk a little bit. Let me talk a bit more about pages so we can understand what exactly page contains, or how is a page organized, right? So a page this is the database page, by the way. What it contains, there is normally a header inside the page. So the header will contain like the page size, it'll contain some checksum, it'll contain the database version, it'll contain some information on transaction visibility. I'll talk about that later. It'll contain some information on compression. So I have a question, right? So what is supposed to be inside this page? We're supposed to have tuples inside this page, right? So basically, you can imagine inside this page, the page has 16 kilobytes of information, 16 kilobytes of space. We want to fit our database rows inside here, okay? So what we want to do is we want to put, let's say you have user, right? I have, let's say 10 users. I want to put each user role inside this page, okay? So I can have 10 users data inside one page, 10 user rows inside one page, right? So a question here, and shall open to the audience, is how should we organize our tuples? Right? Can you guys think of a good way to organize tuples? Yeah. Anyone wants to take a dig at this? How should we organize? How should we structure our rows here? I may have put people to sleep, I realize. Yeah, I'll wait a few seconds for an answer. All right, I mean, so okay, sequentially, yeah, sure. That's a good answer, actually. So that's the first thing that will come to my mind as well. Yeah, you can order sequentially, right? So you can actually just put the rows one after each other, right? So just row 1, then row 2, row 3. Easy, right? That makes sense. There is a problem with that, right? The problem is, in that case, if you need to delete a row, right? How do you delete? Because if you order sequentially, you delete the row, it's like it's a fairly expensive, it's kind of an expensive operation, right? And also you need to, because you need to move everything else to the correct slot, right? So it's a little bit expensive, and in order to find, so you'll have these holes when you delete, right? So it's not that ideal. Does it depend on data type? Each element in the tuple? Yes, that is correct. That so that it does, and in this case, let's assume the data types are kind of static size to make it a little bit easier, right? So let's say you don't need to worry about dynamically sized rows. Although that is another issue that you also need to think about. Like if you have some kind of column where the size can be larger, can be dynamic, then you also need to worry about this. But yeah, it does depend on data type. But let's say data type is fixed, right? And question response I got is in Rust, they organize the data pointed in the stack and actual data in the heap. In the stack, these tuples are sequentially organized. Tuples here refers to the database rows. So the rows in the database, like let's say each user records, right? So that's what I mean by tuples here. So it's not really related to like how the in-memory representation is. Related to the on-disk. So when I'm storing these pages on disk, because I'm storing these pages in disk, right? So I can't have pointers in my stack or heap. This is like how do I represent it in disk, right? So I think the key thing is, however, the ID index linked list is an interesting idea as well. I'll just share how we actually do it. So actually someone else, so Derek actually shared a pretty good one. It's basically what we end up using. It's called a slot array. It's a pretty smart idea. So the slot array, what the key idea in a slot array is, we have some sequential bits. Basically, we have some sequential slots that we add, and the slots point within the tuple. They contain some offset within the tuple that actually point to the actual tuple data. So this makes like deletions quite cheap, and insertions also are quite fast as well, right? So and what we do is we normally fill up the tuples from the end. So this is how many database systems will end up storing things, although this is not the only way, and this depends. But this is like an interesting implementation detail. Yeah. All right. So Jamin mentioned you can delete it by putting a filler. Yeah, you can. Like I said, you can do it. It's not wrong to do it that way. Definitely you can. It's not wrong. It's just not as efficient for different kinds of operations. But definitely, yeah, like I mentioned, it's not the only way. And if you want to design your own database system, feel free to try. There are other ways, right? But this is what MySQL, for example, does. MySQL will do this. All right. Okay. So talk about buffer pool. So someone mentioned very wisely, buffer pool is okay. So sorry, I'll go back a little bit. So why the slot array? So why start in the back? Start on the back. The reason is that you want the slot array to grow from the beginning. So it's kind of like stack and heap in a way. Basically, if I don't start my tuples from the end, then where do I start from? Because I want my slot array to also grow, and I want my tuples to also grow, but I don't want them to, conflict. So one way to make them grow is, grow at different ends, and then when they're full, the page is full, right? So like, another way to do it would be, you can have a fixed offset, I guess, and you could start from a fixed offset. That would be another way. I think that might work as well. Yeah. All right. I hope that answers the question. Okay. All right. Good. Okay. So I'm gonna talk a bit more about the buffer pool. So buffer pool, once again, key idea, very simple, is we want to use LRU to keep the recently used pages in memory as much as possible. All right. So this is very similar to caching. Basically, so what we do is when we get a query, let's say I want to fetch the page 2. What's going to happen is my execution engine, which is my query engine, is going to run that query. It's going to know, okay, I have a page 2. Page 2, I'm going to look up the page directory. I know it's stored at this point. I'm going to look up the page. What I'll do is once I find the page is that slot array thing that I showed you. So the row I'm interested in is in this page. I'm going to look up the page. Once I find the page, I'll load the page in buffer pool, right? And once it's in the buffer pool, then I can run my query on top of it, and then do whatever I need to do, select, find the row, and do whatever filter or whatever other operation I need to do. So the key idea is that the database will use some kind of LRU strategy to put the pages in memory as much as possible. All right. So that's why it's very important to have a very large buffer pool. And normally when you have database systems, if you notice, they would tend to use almost all or a very large amount of memory, and they use it all the time. They won't give it up because this is basically all kind of pre-allocated by the buffer pool. And for InnoDB in particular, the way it works is they have a kind of a list. The way the buffer pool is organized is they have a list where they'll keep track, where they will insert pages in the middle, and then they have some kind of eviction strategy for all pages. So you guys can read up the more details for InnoDB. I won't mention it. I won't put too much details on it for now. All right. Before I go there, there's a question on what happens if the size of a tuple exceeds the width of a page header. In that case, you can't fit it in that. You shouldn't. The database system should not insert it in that tuple. You should not insert it in that page. You would insert it in a different page. Right. Buffer pool same as cache. As someone else mentioned, yes, it is essentially like a cache. It's just that the difference is the buffer pool is kind of doing a bit more work than a simple cache would, but you can think of it as a cache. Yes, you can think of it as a cache. It is essentially a cache. Yeah. All right. How will learning about this translate into practice in software development? So this is very important because it's very important for you to understand why a database system runs this way, right? So, and how to speed up queries, right? So for example, if you have a query and you realize that the query is slow, right? So how can you optimize it? Right? So I'll give you a very good fun example of this. So one fun example where the LRU algorithm is not that good, and this can cause your queries to be slow, and then as an application layer developer, you will feel the pain, right? So one example of this is, let's say you have a query let's say you have two kinds of queries. So you have one kind of query that's actually doing that actually is doing a lot of, let's say, lookups, right? So it's fetching single rows from the database. The QPS is very, very high, right? But the cache hit rate is pretty good. So most of the time, the query latency is very low. So let's say, for example, maybe 99% of the time, the query latency is less than is in 1 millisecond, because the cache hit rate is 100%, almost 100%, right? So let's say you have this scenario, or let's say 99% cache hit rate or whatever, very high cache rate, low latency, very beautiful scenario. This is what you want. And then you do a query that does a very large scan. So let's say you have some query that, let's say you did some backup. You did a backup at that time, for example, right? So when you do a backup, or you do some query that does a very large scan, what happens? What happens in LRU? What happens in LRU, right? If you just have simple LRU, what will happen is it'll replace, right? It'll dirty your cache. So your cache that was so nice because of that heavy workload, you will start losing those values, right? So your cache hit rate will slow down. Now you have to go to disk to fetch. So that large QPS you're getting will start hitting disk when you're running that query that does a large scan, right? And then that'll slow down your queries, and your latency will spike up. And that'll spike up a lot. So if your cache hit rate drops, it has a very big impact on your query latency. So you have to be mindful of this, and you need to understand, okay, so how can I optimize this query, and whether there's something I can do about this. So the good news about this is that actually it doesn't use a simple LRU strategy. MySQL will use this thing called LRUK. So it'll keep the K most items as far as I know. And there's ways you can optimize the query if you have this kind of scenario. So my key point is it's important to understand these things in depth, so you can answer these questions and optimize your systems for a production workload. So because in a production setting, in a high performance setting, it's very important to understand why your database is not working as it should be. All right, so won't using smaller queries maintain cache hit rate, increase the number of IO calls? No, it won't. If your cache hit rate is good, you don't need to hit the hit IO at all, right? You only need to go to memory. You don't need to hit the disk because everything is being fetched from cache. So that's pretty good. IO is slow. Disk IO is quite slow. All right. In relation to above question, during initial software architecting, is it all about analyzing this implementation about DB engine? Do we need to read the DB manual? So not exactly. It's good to know this. And as a senior engineer, normally, especially, it's highly expected for you to know this. Normally, the main thing you need to know is when you're doing when you are designing a schema, and you should lay out your queries. So what are the most common queries? How fast would they be, right? So these you should know, and whether they would use whether they would use an index, and whether they would be fast or not, and how fast they would be. It's important to know. Usually these details actually, they come up not at the architecture stage, they come up more when you're doing debugging, or more when you're having production incidents. So I can share a lot of horror stories here if I have time. We had an incident. We have several database related incidents. We had one a few weeks back where basically the database acquired some lock longer than it had to, and that led to query slowdowns. And we had to spend a long time investigating why, and it was because some of our queries were not as optimal, right? So usually when you're troubleshooting, especially large scale at a large scale, this becomes more relevant. And normally that's the time when you're going to do a deep dive to understand what's going on. Okay, all right. Okay, so I'll talk a bit about B+ trees. Can't get any database talk without B+ trees. So normally indexes, when you create an index, let's say you create an index on a particular column because you want to speed up the query. There's different kinds of indexes. There are hash indexes and tree indexes. Tree indexes, I talk about B+ tree indexes in particular. B+ tree indexes basically are used to store sorted data. And normally the structure of B+ tree is, what is a B+ tree? B+ tree basically is, if you use the binary tree, like AVL tree, is basically that, but it's a generalized version. Instead of having only 2 nodes, 2 children, you will have n children. Normally n will be a pretty large number. Normally it's I think it's the block size basically. So yeah, it's a very nice data structure because you get logarithmic search. So it's beautiful. Normally what happens is you'll have these leaf nodes and inner nodes. So inner nodes basically contain pointers to the leaf nodes or to other inner nodes, depending on your level of nesting. One thing that you would also have is you'll also have these pointers between sibling nodes. This is to make scans faster. So especially in the leaf nodes, you'll have some pointers to the sibling. So if I want to do a full scan, I don't need to go to the parent. I can just continue scanning through the leaf nodes. This is quite nice. This is a little bit about B plus trees. B plus trees have certain kind of balancing algorithms. I won't talk about that right now. They can be fairly complex, but just be aware that when you create an index, you normally you can find out the details of the index from MySQL from DB, but many of the times it would use what's called a B plus tree, and B plus, this is what B plus trees essentially do, right? There's other kinds of indexes as well, like hash indexes as well, and they're also used for certain kinds of scenarios. All right. Okay. So when you have a B plus tree, what to store inside the node, inside the leaf node, right? That's a design question that some databases, different databases have different like answers for, and this has different performance implications and may affect your choice of database as well. So this is one big difference between Postgres and MySQL, for example. So in Postgres, what the leaf nodes store actually are record IDs. So what happens is actually the index only stores the record ID. So if you want to get the actual record, you need to do an additional lookup to the record ID. That's what Postgres does. In MySQL and some other databases like SQLite, they actually store the tuple itself inside the index. However, this means that so this is why in MySQL, when you create a primary key, the primary key is actually an index, and so the primary key itself will be a B plus tree, and the leaf node will actually contain the tuple itself. So that's why it's also one of the reasons why in MySQL the primary key lookups are quite fast. However, if you have a secondary index will use some record ID as its value. All right. Okay. All right. So I'll talk about the final stuff. Transactions. This is one of my favorite things. And this is the part that is very relevant to application developers. And this is something that people miss out a lot, and people make a lot of mistakes around this. Okay. So key idea behind transactions is we want to make sure we want to surround consecutive SQL statements and execute them kind of atomically, right? So what we do is we surround the SQL statement with begin and commit to achieve what's called ACID transactions. What does ACID mean? So in ACID, A stands for atomicity. That basically means that either all succeeds or none succeed. This is very important. And this is this guarantee is very underrated, because it's actually a very important guarantee. And this is the biggest advantage of systems like MySQL that give you ACID transactions. If you use like some kind of NoSQL system like Redis or MongoDB or something, you don't get this or you don't get this for multiple rows very easily. And this is this makes writing a lot of application code simpler and correct, because there's a lot of things that can go wrong if you don't have these guarantees. So you can imagine, like in my kind of use case, where we're dealing with money and balance, you want to make sure when you're doing a transaction, you deduct and then you credit, right? So you deduct someone's balance and then you credit someone else's balance. This must be atomic. If it's not, we lose money, or someone loses money, right? So this is very, very critical. So that's why atomicity is very, very important, and ACID transactions are very important to guarantee this. And the C stands for consistency. This means that after you write, the read should be consistent. So it kind of makes more sense in like a distributed setting, but this basically means that if I write to your database, if I read afterwards, I should get the same result. Isolation is one of my favorite things to talk about. So basically what this means is what happens when you have concurrent transactions. So let's say I have two transactions that update someone's balance, right, that happen at the same time. Then what's going to happen, right? So these should not impact each other, and that's what isolation means. We'll talk a bit more about isolation in a bit. And durability, that all the data is persistent to some non-volatile storage. So if I plug out the power, I don't lose data, basically. So, but a question: how do you keep data in duplicated databases in sync in active replication? This is a loaded question. So active replication is so one thing, I don't recommend using active replication unless you know what you are doing and you can guarantee there are not going to be any conflicts. If you're using active replication, you must have a way to deal with conflicts, because otherwise I don't recommend it. And if you have a way to deploy, if you have a way to handle conflicts, then it depends on your conflict resolution strategy, right? So it depends on your architecture. In ByteDance, we do use active for some use cases. But in those cases that require strong consistency, we tend to avoid it. All right. What if one transaction is dependent on the other? Does it mean it's not a good transaction? Like if you don't do event A, you cannot do event B. What? Right. I mean, no, I think that makes sense to be in a transaction. So if you have this kind of, although it doesn't, this case, if it's just about, okay, so it depends on what you're trying to do, to be honest. To give a slightly more concrete example, but if you must guarantee that event A and event B must happen together, right? And if they cannot happen separately, like you cannot have event B without event A, then in that case, transaction makes sense. However, if you just have a linear thing, then it's not necessary, right? I mean, then in that case, your application layer code can also guarantee, right? So if you have event A and only then event B, and you don't need this to be atomic. So you can have a situation where you have event B without event A, event A without event B, and this is fine. Or you have event A and then you get event B eventually, that's also fine. So it depends on the amount of consistency you want. So it really depends on your database design and what kind of consistency guarantees you can live with. But if you want to guarantee that definitely if you have event A, you must also have event B or nothing at all, then in that case, you should use transactions. All right. Got a question on, even in a single database, how do we ensure data is sync? If a column is updated, is duplicated, aka exists in another table, do we have to lock all relevant rows in their respective tables? Yeah, okay. Normally, for when you're doing database transactions, normally what happens is you will be operating on rows, right? And if you have concurrent access on rows, normally databases would get row locks normally. So InnoDB will get locks on the rows and will lock, and basically the row lock. So it depends on, okay, so for locking, it depends on what you're exactly doing. There's different kinds of lock granularities. Normally, if InnoDB will try to make sure you use row locks if it can. If you can't get row locks, it'll try to use something what's called intention locks, mostly cursor locks, basically. Maybe a table lock if it has to, especially if you're doing some modification on the data schema itself, then it definitely has to use a table lock. So column lock is a bit more like, because it's a row-oriented database, column lock usually is usually how I would do it. Yeah. And I got a question on read after write consistency chosen for ISA transactions. It doesn't have the consistency for models such as for write, follow, reads. What do you mean by write, follow, reads? So when I say, okay, consistency, the term consistency in ACID is a little bit funny. I read from one this guy, this CMU lecturer in CMU. He mentioned that the C is actually just thrown in there to make the catchphrase sound better, because ACID sounds better than AID. Because actually the consistency here is not that strongly defined. I give read after writes as an example. It's not for how it's defined formally. But what it means here is that data is consistent in the sense that, yeah, in the sense that it's when you store something, if you access it later on, you'll get what you expect. All right. Okay, got a question on the B plus tree. Okay, I'll go back to it for a bit. So here's the B plus tree, and just to share like what it's storing is basically the B plus tree is storing the key. The key here is the thing you're indexing on. So let's say in this case, let's say it's the age. Let's say I'm indexing the age, and let's say these numbers are ages, right? So what happens is if I want to do a lookup on, hey, I want to find a value where age is 1, what I would do is, okay, I would go to the first node. I see, okay, I want to go look for 1, right? So 1 is less than 5. There's a pointer inside. The pointer points to this node. So I'm going to go to this node. Then I'm going to search to this node and say, okay, I found 1. So inside 1, 1 is a value leaf node. The leaf node basically contains the value inside as well. So I'll just look up the value. The value will be my tuple. I can just share my tuple, for example. All right. So that's basically how the index works. All right. Hope that makes sense. If I want to do a lookup for, let's say, 7, I'd go to 5. I'd see it's greater than 5 and less than 9. I'll follow the middle pointer here, and then I'll go to this middle block, middle node, and then I'll search through this one and I'll find 7. All right. Okay. I hope that answers the question. And another question on B tree, that some databases didn't use LSM, others use B plus tree. Yes, that's correct. So B plus tree is okay. So usually database engines will use different kinds of data structure. So B plus tree and LSM trees are different data structures. And so InnoDB is a database engine that tends to use B plus trees for indexes that require sorting, that require ordered indexes, right? So that's but it's not the only kind of data structure it uses. It also uses hash indexes, for example. But InnoDB tends to use B plus trees quite a lot. So InnoDB could have used LSM trees, but they don't, right? So LSM tree is another way to store ordered data. So and some other kind of databases like RocksDB, the storage engine, will use LSM tree to store this kind of ordered data. So LSM tree is a data structure, B plus tree is a data structure, InnoDB is a database engine, RocksDB is a database engine. I hope that makes more sense. All right. Okay. B plus tree for indexing, why not use hash table where lookup is 01? Great point. Hash tables can't do range lookups, right? So if you want to do a query for less than or greater than, you can't do it. You can't do it in hash indexing. It's impossible, right? So there's certain kind of queries where, so if your query is only equals, then a hash index kind of makes sense and might be faster. But if your query is involves some range lookups or range queries, you can't do it with hash index. That's one of the reasons why you want to use a B plus in tree. Okay. B plus tree versus AVL tree, or like a binary tree. Yes, that's correct. So because B plus tree have a very large number of children, it's very good for cache locality. That's also another reason why we would prefer to use B plus tree. Another reason for using B plus tree is because it's the same concept that we talked about earlier, sequential access, right? So normally we would optimize the node to be the same size as the page. So this node itself will be a page basically, and that is quite fast because actually our lookups are distributing pages from our block storage, so it's quite fast, right? Okay. Updating the age column in table A, table B, age column 2. Oh, in this case, no, this is a different case. In this case, you need to handle this in a transaction then. So you need to update both in one transaction. Attendance form been sent yet? I don't know about this. Maybe Mutomi can help answer this one. All right, reaching the end. I'll try to hurry up. Okay. So talk about transactions. Okay, so I'll talk about isolation a little bit. So this is last couple of slides. So isolation basically means how much the transaction is exposed to the actions of other concurrent transactions. And usually the trade-off here is you can have greater concurrency if you can expose your transaction to more changes that are happening. There's different kinds of isolation levels, and these will expose you to different kinds of bugs when you have high concurrency. So we have this isolation level called, so we have different kinds of bugs that'll happen. So one kind of bug is called dirty reads. Dirty reads basically means that even though you have not committed your changes, someone can read those. Someone can read them. So that means if you have two transactions, right, but they didn't commit yet, so stuff from transaction A might be visible to transaction B. So if that happens, it's a dirty read, right? Because it's dirty because the transaction may not be committed. Maybe it'll roll back. So you read something that was invalid. So this is a bug or a phenomenon that can happen. Similarly, this thing called unrepeatable reads. This is a bit more complex to explain, but basically what it means is that you read the same data again within one query and you get different results. And this can happen. And this can happen basically because that thing might get updated while your transaction is running. If you have a long transaction running, so for example, you take a DB backup and you read something multiple times, maybe you find different values because someone else updated it, right? And this can be problematic. Another very complex one to explain is called phantoms. This one is basically rows that match a predicate may change because of concurrent inserts and deletes. I won't spend too much time explaining this, but basically, if you're doing some, if you have some condition that you want to guarantee globally, and this, like for example, you want to make sure that, let's say, the total number of money inside the whole system is a certain number and it should never increase, and then you want to make sure this is always true, and if you do some insertions or deletions, this may not be true. This may change if you if you don't handle this thing correctly. So these are just different phenomena that can happen. I will not talk about it too much in depth. And there's different kinds of isolation levels that are meant from a database that are in database transactions that are designed for you to handle these. So read uncommitted is that anything might happen. It's also the fastest. So read committed means that phantoms and unrepeatable reads may happen, right? But dirty reads will not happen. So which is normally a decent trade-off. So in ByteDance, we tend to use read committed quite a bit. It's good for performance. Repeatable read is the default in MySQL. So this only allows phantoms. Serializable is the slowest. Serializable basically is like equivalent to as if every transaction occurs by itself, individually, one by one. Doesn't actually happen under the hood, but actually uses some kind of locking mechanism. But in this case, you will have no problems. But in this case, the performance is also the worst. So this is a trade-off you have to make in how much isolation you want versus how much safety you want versus how much performance you want, right? This is also quite important, especially for more complex scenarios. Okay, that brings me to the end of the thing. I'll just answer a few more questions.